Hello, my dear students. A very good morning to all the students over here. And my name is Kishore, and today we are at the end of this chapter, that is electrochemistry. We have one more topic to deal with, that is electrochemical cells, or the galvanic cells, or we can call them as voltaic cells. We have seen clearly in the previous session, we have seen clearly about the electrolytic cells, and we have applied Faraday's laws of electrolysis, first law of electrolysis and second law of electrolysis, right? And today we are going to learn about the galvanic cells. How can we generate electricity? How are we getting out the electricity out of a redox reaction? How are we going to use a redox reaction to get to prepare a cell? Using a redox reaction, we are going to prepare an electrochemical cell, and from that electrochemical cell we are getting out the electricity out. Okay, so let's see how are we going to make a voltaic cell and how it works. So let's see what is voltaic cell today. So today we are going to learn about galvanic cells. So galvanic cells, and there we'll be learning about electrode potential, and there is the last important topic, that is Nernst equation. So this is a very important topic, which I would say, so this is the most important topic of this entire chapter. Okay, so if they have to give you any kind of question, whether it is an easy, moderate, or of advanced level, that could be asked from this topic, that is Nernst equation, and it is used to calculate the EMF of a cell, that is the electrode potential of a cell. Okay, the voltage of a cell, we measure it with the help of Nernst equation. So this is very, very important, because to tell, when we talk about the cells, it is the potential that they would produce. So how much electricity are they able to produce has been calculated with the help of Nernst equation. So this is the most important topic of this entire chapter. So you will be getting a lot of questions from this Nernst equation. Okay, so let's start with this galvanic cells today. Right. So what do we have to learn? So as I have told you already, electrochemical cells are the ones which work on redox reaction. And redox reaction, there are two parts, that is reduction happening and oxidation happening simultaneously. So there is reduction and oxidation happening simultaneously. So this is the oxidation. So we have separated both the reactions, both the parts of the reaction, that is reduction and oxidation, into two half cells called as oxidation half cell and reduction half cell. So there will be loss of electron at the oxidation half cell, and there will be gain of electron towards the reduction half cell. So that is how the cell works. So there is a flow of electrons, and this constitutes the electricity, nothing but the voltage difference. So you can see the bulb glowing over here, right? So this is how we are going to make use of redox reaction to generate electricity, right? So this is what we are going to learn. And in the galvanic cell, we have the most important parts. So the two parts I have already told you. The two parts are the oxidation half cell and the reduction half cell. Apart from oxidation half cell and reduction half cell, you have the voltmeter to calculate the voltage difference, and you have something called as salt bridge. So we will be learning about salt bridge in the next few slides, right? So are you clear with this electrochemical cell? So this is your electrochemical cell, where there is a flow of electron and you are getting the output in terms of voltage, right? So when we are learning about electrochemical cell, in our chapter we always take the example of Daniell cell. Okay, so this is the Daniell cell, which is the most simplest cell, or we can say the example which we take is always a Daniell cell. So what is a Daniell cell? How do we make an electrochemical cell? Okay, what is that? With the help of a redox reaction. So here the redox reaction happening is over here. So in this solution, it is like a metal dipped in its metal solution. How do you make a half cell? To make a half cell, we need to take a metal electrode dipped in its solution. So we take a zinc electrode dipped in its solution, means in its ionic solution. It means it can be ZnSO4, ZnCl2, anything. So a metal electrode dipped in its salt solution, in its salts aqueous solution. In the same way here, copper dipped in its solution, copper sulfate solution. So this is how you have to make your half cells. This is your oxidation half cell, and it is a convention. It is the conventions that we use is always we write down the anode and then cathode. Okay, it's not your wish to write anywhere anything. No, we always write the conventions. If you go according to the conventions, we always write down the anode and then followed by cathode. Anode compartment followed by cathode compartment. Okay, and you can see there is a salt bridge over here. So I'll tell you the importance of this salt bridge for right now. What is that? Zinc dipped in zinc sulfate solution, copper electrode dipped in copper sulfate solution. So these are the two half cells which we have, and this is the salt bridge. And these two half cells are connected by a wire which passes through the voltmeter. which will tell us about the flow of electrons in terms of voltage. Right then. So this is your Daniell cell. So let's clearly see what is happening in a Daniell cell. So if you can see in this Daniell cell, so there is oxidation happening in this oxidation half cell and reduction happening in reduction half cell. Zinc dipped in its zinc sulfate solution, copper dipped in its copper sulfate solution with a salt bridge, right? So what is happening? How these electrons are flowing? You already have seen a glimpse of this oxidation and reduction when we were learning about electrochemical when we were learning about electrolytic cell, right? I hope you guys have practiced. You have learned clearly the basics. What is oxidation? What is reduction? What happens during oxidation? Whether it is loss of electron, gain of electrons, where the electrons are flowing from where to where, right? So these all things again we are going to see there is a small difference here. So what is the small difference? I'm going to show you. So first we will see what is happening in oxidation half cell and reduction half cell. So let's see first in oxidation half cell. Okay, so this is called as the oxidation half cell. It means at anode. Okay, I already told you AO and CR, right? This is your anode and this is your cathode. So which one shall we start? Shall we start with the cathode part or the anode part? At cathode and at anode. Okay, at cathode what happens? Tell me. At cathode reduction happens. This is what I have written last time. At cathode CR. Okay, Cristiano Ronaldo. So CR. So at a cathode reduction happens. Okay, so and what is reduction? Tell me. What is reduction? What is reduction? Gain of electrons. And what is happening at anode? At anode we have loss of electrons, that is oxidation happening. So there is oxidation happening at anode and reduction happening at cathode. So loss of electrons, there is a loss of electrons. Okay, loss of electrons. So we have seen in electrolytic cell who is losing electrons and who is gaining electrons, right? So here we will see who is losing electrons here. Here the metal itself will lose electron. Can you see over here? So this metal electrode zinc, so this zinc electrode which is there, okay, the zinc electrode which is there, I will write this as solid. This is the electrode. This is the electrode part. Okay, so this is the electrode part. What is happening to zinc? Tell me. Zinc is converting into Zn+2. Okay, zinc is converting into Zn+2. This is converting into Zn+2 aqueous plus 2 electrons. So what is happening here? Oxidation. So zinc is undergoing oxidation. So that is what is happening. The electrode is undergoing oxidation. The electrodes are undergoing oxidation. What about electrolytic cell? Tell me. In electrolytic cell, you have seen during electrolysis, it is the ions which are undergoing discharge. The positive ions go and discharge, and the negative ions are going and discharged. Okay, so that is completely different. So that is the ions who are participating, and here it is the electrode. The electrode is undergoing oxidation. Okay, clear with this? Anode, at anode we have oxidation happening and zinc is converting into Zn+2, giving out the 2 electrons. So these 2 electrons now, so this zinc converting into Zn+2, you can see over here. So this zinc converting into Zn+2 and you have these 2 electrons traveling towards your cathode. You're getting this point here? So these 2 electrons are going to travel towards your cathode. Now what happens at cathode now? So these 2 electrons which are going towards the cathode, what is this? Gain of electrons. Gain of electrons by whom? The electrode. Okay, so what is the electrode here? We have the copper electrode, copper solid. We have the copper electrode, and what is happening? Tell me. So here you can say, yeah. So here you can write this as Cu+2. So these 2 electrons will be taken away by whom? So these 2 electrons are being taken away by the copper plus 2 ions who are there waiting for the 2 electrons. So absorb, they will grab these 2 electrons. So the Cu+2 ions which are there in the aqueous solution will give electrons. Okay, they will grab these 2 electrons and convert into copper accumulation. So there will be an accumulation of copper. So you can see here dots. Can you see the dots over here? So there will be an accumulation of copper over here. So there is an accumulation of copper over here. And what is happening to the zinc electrode? What happens to the zinc electrode when this process is continuing? If this oxidation continues and if this reduction continues, what happens finally? What is the final situation you will see? You will see that the zinc electrode which is there will slowly get deteriorated, will slowly get dissolved. The zinc electrode will slowly get dissolved, and what is happening at the right hand side? In the cathode compartment, the copper gets accumulated, and the weight of this electrode will go on increasing. So this is what is happening. So there is a dissolving of this electrode and accumulation over this electrode. So what is happening here? So here we are seeing oxidation, electrons coming out, loss of electrons, and these electrons are being taken by the copper plus 2 ions, which are present in the solution. So this is how the cell is working. Okay, so this is how the electrons are transferring. Fine. So we have learned how the electrons are getting transferred from this half cell, the oxidation half cell. This is called as the oxidation half cell. Oxidation. Why we are calling it as a half cell? Because it is together. When we combine this together, we will get a redox reaction. I'll show you that. So this is the oxidation half cell, and this is the reduction half cell. Oxidation half cell and reduction half cell. Why we call them as a half cell? Because when we combine them, this complete together, this process, the oxidation happening here and the reduction happening here, together when you combine, they will give you a redox reaction. I'll show you. Suppose if I write down both the reactions together. So what are the two reactions which I have written? So there is oxidation happening here, right? There is oxidation happening here and reduction happening here. So what are the two reactions that we have seen? So zinc converting into Zn+2, right? Zinc converting into solid, converting into Zn+2, aqueous, plus 2 electrons. This is at where? Tell me. This is at cathode. Okay, this is at anode, right? And then what is the next reaction we have? This is at anode, and at cathode what is happening? The copper plus 2 ions in the aqueous solution grab these 2 electrons and they get accumulated as copper electrode. So this is what is happening at cathode, and this is at anode, right? So at cathode, at an anode. So now when I combine these two processes together, so what I will be getting? So you know that same things on the right hand side and left hand side will get cancelled in a chemical equation. So you have 2 electrons on the left hand side and 2 electrons on the right hand side. So these 2 will get cancelled, right? So same species on the left hand side and right hand side will get cancelled over. So I have cancelled the 2 electrons which are on the left hand side and on the right hand side. So what is left over? It is the final reaction is what? Zinc solid plus Cu plus 2 aqueous, giving you Zn+2 aqueous plus the copper. So this is the final equation that I'm getting. And tell me whether this is an oxidation reaction or reduction reaction. What kind of reaction is this? What is happening here? You can see zinc is undergoing what? Tell me. Zinc is undergoing what kind of reaction? This is oxidation. Zinc is undergoing oxidation. And what is happening to the copper? Copper is undergoing, what is happening? From +2 it is going to 0. So this is reduction. So zinc is undergoing oxidation number increasing from 0 to +2, and copper undergoing reduction from +2 to 0. So there is oxidation, increase in oxidation number, and reduction, decrease in oxidation number. So you can see 2 reactions happening simultaneously. And what is this reaction now? This is a spontaneous redox reaction. When can I call this reaction as a spontaneous? See, this is the redox reaction. When can I call this reaction as a spontaneous redox reaction? If its delta G, is less than 0. You have learned this in your thermodynamics. So a process can be called as a spontaneous process if its delta G, Gibbs free energy, is less than 0 or negative. So this reaction can be called as a spontaneous redox reaction. And because of this spontaneous redox reaction, what is happening? Tell me. There is a transfer of electrons. How many electrons? 2 electrons from here to here. Okay, clear now everybody? I hope you guys are clear with what is a voltaic cell, what is the process happening. So you should learn how to write down each compartment. Like you should know how to write down the oxidation half cell. You should be knowing in this chapter, it is must. From now onwards, you have to learn this. What is that? You should know how to write down the oxidation half cell and the reduction half cell. Both the half reactions you should know how to write. And how do we get the actual reaction which is happening? You combine them. So when you combine this oxidation half cell and reduction half cell, what I have done here, I have combined both the half cells and I got my complete cell. So this voltaic cell runs on which reaction? Tell me. This reaction. Okay, see, I have written you, some of you might be getting confused with this Cu plus 2 aqueous. Cu plus 2 aqueous means nothing but it should be, it is a copper sulfate. Let's say it is a copper sulfate solution. So zinc plus copper sulfate will give you Zn plus 2 means nothing but ZnSO4. Zinc plus copper sulfate gives you zinc sulfate plus copper. So that is how I have written. So this aqueous solution can be anything, any salt solution of copper. You get this point here? So this is your Daniell cell, which is a voltaic cell, and usually it is seen that the voltage generated is around 1.1 volts, 1.1 to 1.12 volts around. So I hope you guys are clear what is a Daniell cell and how it is working. So till now, what are the things we have learned? We have learned what is a Daniell cell, how it looks, what is oxidation half cell, what is reduction half cell, what is happening in an oxidation half cell, and what is happening in a reduction half cell, and how can we combine together to get a complete voltaic cell. So that is what we have learned. Okay, there are few things now, few doubts I get. So as I have told you in the previous case, as this cell is working, as this cell starts working, what is happening to the oxidation compartment? The electrode is getting dissolved. So the zinc electrode which is there will slowly get dissolved. Dissolving is something like you have your ice cream, right? So if you hold your ice cream for longer time, what happens? It will dissolve. So it will become smaller in size, right? So that is called as dissolving. So this electrode which is there will get dissolved. Slowly it will vanish. And what will happen? Tell me. The copper which is there will get accumulated, become heavier and heavier. So what happens now? Okay, will this process happen? What will happen later? So if this will get dissolved completely, what will happen? Finally, the cell will stop working. So this is what is happening. So to avoid that, and one more thing, if you can observe here, see here what is happening. Tell me. The zinc is converting into Zn plus 2 ions. Can you see here what is happening? The zinc which is there, okay, the zinc electrode which is there is converting into Zn plus 2 ion. So if this process is increasing, what is happening? Tell me. As this oxidation process is happening, what is oxidation process? This is the oxidation process. So as the zinc is getting dissolved, slowly this will get dissolved, and this will convert into what? Tell me. Zn plus 2 ions. It means the Zn plus 2 ions will be increasing in this solution. Are you getting this point? As the cell starts working, after some time you will see that the zinc is getting dissolved, and the Zn plus 2 ions in the aqueous solution will increase. So they will increase. The Zn plus 2 ions will start increasing. Okay. So once this Zn plus 2 ions will start increasing, and what is happening to the reduction compartment? Tell me. So this Cu plus 2 ions. So these Cu plus 2 ions which are there in the solution, the Cu plus 2 ions which are there in the solution now, what is happening to the Cu plus 2 ions in the solution? They are getting accumulated as copper. It means this copper accumulation will increase, and this Cu plus 2 ions will slowly become lesser. The concentration of Cu plus 2 ions will decrease. So what is the final statement which I want to give you is that as the cell is working, the concentration of Zn plus 2 ions will slowly increase, the concentration of Zn plus 2 ions will slowly increase, and the concentration of Cu plus 2 ions will slowly decrease. This is what I'm going to point out. So as the cell is working, what is happening? As the process is going on, there is an accumulation of Zn plus 2 ions, and what is happening? There is a decrease in the concentration of copper plus 2 ions. Everybody clear with this? So there is more positive ions in this half cell, and what you can say here, see, this is copper sulfate solution, right? Copper sulfate solution means along with this, what else is there in this? Sulfate ions. So as the concentration of Cu plus 2 ions is decreasing, what is the other way of thinking? Concentration of positive ions is decreasing means we can say the concentration of negative ions is increasing. It means, what is the point which I want to highlight is here the concentration of positive. So here it becomes more positive in nature, this concentration, and this becomes more negative in nature. Okay, this will become more negative in nature. So this cells will have an accumulation of positive ions, and you can say here we will have an accumulation of negative ions. Okay, so clear? See, now one more logic you can see here. See, what is this compartment? This is your anode compartment, right? This is your anode and this is your cathode. What is the charge of anode here and what is the charge of cathode here? Can somebody tell me what is the charge of anode and what is the charge of cathode? Yes, can somebody give me the answer? What is the charge of anode and what is the charge of cathode in this voltaic cell? So if you can see here, so there is generation of electron, there is a formation of electrons, zinc converting into Zn plus 2, and you can see there are 2 electrons over here. So this electrode which is there is negatively charged because of the presence of electrons. So here we have the electrons present. Okay, since you can see these electrons, this electrode is able to generate the electrons. It means this is negatively charged. In this way you have to identify. So this electrode is generating electrons, means it will have negative charge and it is moving towards a positive electrode. Is that clear, everybody? So this is what you have to find out. Okay, you have to be very clear about the electrode charge also. So this anode is negatively charged and this cathode is positively charged. Okay, now if you can see, these two are contradictory. Can you see this contradictory? What I told, this anode is negatively charged and this cathode is positively charged, and as the cell is working, what is happening? There is accumulation of Zn plus 2 ions and the positive charge is increasing, and there is accumulation of negative ions and the negative charge is increasing. So what is happening, tell me? Finally, because of this accumulation, the cell will stop. The cell comes to end. Why? Because there is an opposite potential applied. Okay, two opposite potentials applied, the cell is dead. Are you getting this point over here? So as the cell is working, so there is some restriction to this. What is the obstruction? What is the thing which is affecting its working? The generation of, see, if there is no generation of this positive and this negative, then the cell will continue working. So the only problem faced by this electrolytic cell is accumulation of Zn plus 2 ions here and accumulation of sulfate ions, or increase in the concentration of Zn plus 2 ions and decrease in the concentration of Cu plus 2 ions. So because of this, there is accumulation of positive charge and accumulation of negative charge. Because of this, what happens? There is something called as junction potential. There is something called as junction potential created, which will stop the reaction happening. Okay, which will stop the reaction. Once the reaction stops, if this reaction stops, what happens? Finally, the cell will stop working and there will be no bulb glowing. So that is the problem faced in the initial days. What is the problem faced? Because of the accumulation of charges in their respective half cells. So what is the solution for this? So how can we avoid this accumulation? So this accumulation can be avoided with the help of salt bridge. So we have the salt bridge to overcome the problem faced during accumulation. So the accumulation of positive, so there is an accumulation of positive charge in this compartment and there is accumulation of negative charge in this compartment. So we have to neutralize that effect, and that neutralization is being taken place with the help of salt bridge. So what is this salt bridge now? So this salt bridge which is there, it is like a glass tube which is filled with a jelly kind of substance, gelatin kind of substance, in which you will have a salt present. So what type of salts we are taking? We take an electrolyte which is like KCl or KNO3. So what is the work of this salt which is present in this salt bridge is that whenever there is an accumulation of charge either in this compartment or in this compartment, these salt, which are good strong electrolytes, the KCl, K plus ions and Cl minus ions, which are present in this gelatinous liquid, so they start moving to their respective. Suppose there is a accumulation of positive ions, so what will happen? Tell me. The Cl minus ions or the NO3 minus ions or the sulfate ions will start moving through this. So whatever the negative ions which are present in this will start moving to their opposite end. So all the negative ions will start moving to this, and what they will do, they will neutralize the positive charge accumulated, and the positive ions will move towards the other end and they will neutralize the excess negative charge developed here. So in this way, the salt bridge is able to neutralize the effect of junction potential. Are you clear with this? So salt bridge is very, very important. What is the need of salt bridge? Tell me. For the continuation of the cell. See, Once we connect this cell, the cell starts working. The cell starts working, but after some time, what happens? Because of the dissolving of the electrode and accumulation of this electrode, there will be a junction potential created, and finally the cell potential, you can see the bulb will start flickering and flickering, and finally it stops. So to avoid that, we have a salt bridge to extend its working. Okay, if it is able to work for 1 hour, if with the help of salt bridge, it will work for another 3-4 hours. So that is how we have extended the battery life. We have extended the battery life by removing the junction potential. So that is the work of salt bridge. Okay, clear with this? And very important that there are some conditions for this salt. You can't take any kind of salt. You have to take those salts which are a strong electrolytes. They are strong electrolytes, and they should have same mobility. The K plus ions, suppose if I take KCl ion, okay, KCl salt, so this will be always present as K plus and Cl minus, right? So these ions, the potassium ions and the chloride ions, will move to their respective junction potential areas, and they should move in an equal rate. The mobility, the rate of mobility should be same. You have to select those salts whose rate of mobility is same. Because suppose, so the K plus ions are moving towards this, the K plus or the Cl minus ions are moving towards this compartment, and the K plus ions are moving towards this compartment. If the rate at which they are moving, if it is not equal, still the junction potential will be there. Still the junction, there is neutralization of the charge, but it won't be that efficient. You should take a salt which is having ions which have equal rate of mobility. So they should be able to move to the respective electrodes at equal rates. So how, at what rate? K plus ion is, suppose 10, within 10 seconds, suppose 10 Cl minus ions are entering into this solution. In that 10 seconds, you should have 10 K plus ions entering into this. So the neutralization process should be at the same rate. Otherwise, the junction potential will still remain. So that is the main condition for the kind of salt that you take, and it should be an inert salt. Okay, right. You can see in this animation over here. So this is a copper sulfate, copper in its sulfate, copper sulfate, zinc in its. So you can see the zinc. Can you see this over here? The zinc has dissolved, and there is accumulation of copper sulfate. Okay, so that is how. So there is buildup of negative charge in this compartment and the buildup of positive charge, Zn plus 2 ions. There is more Zn plus 2 ions, there are more sulfate ions into this. So what happens? Because of this, the cell will stop working. So what we have done to avoid the accumulation of charges, we have put the salt bridge. So this salt bridge, what they will do, this will send all the positive ions into this and negative ions into this, and it will neutralize the effect. Are you getting this point? So this is the use of your salt bridge. I hope you guys are clear with this concept of salt bridge. So what is the use of salt bridge? So what are the uses of salt bridge? You can see over here. So how the sulfate and copper K plus ions are moving to the respective half cells. Right. So what are the uses of this? So it completes the electrical circuit. That is one more important point. So there is a flow of electrons from here, and it is stopping the junction potential, means nothing but there is a continuation. So this is the continuation with the help of salt bridge. Can you see? So the electrons moving in this, the positive, there is a movement of ions in this, and again movement of electrons. So this is how there is a continuation of this electrical circuit. So the circuit completes with the help of salt bridge. If there is no salt bridge, still there is a reaction happening, still there is potential developed. Okay, still there is electricity generated, but it is not for a longer time. Okay, this will stop working after some time. If you have a salt bridge, this process will continue. And there is no accumulation of any charges in any of the cell. Okay, what is the next use? The next use is a salt bridge helps in maintaining of electrical neutrality. That is what our removal of junction potential. Removal of junction potential is nothing but neutrality, maintaining the neutrality. There is one more use of this. What is the next use? It stops the accumulation of charges. Yes. So this is the use of your salt bridge, which helps in the continuation of the cell. Right then. Okay, once we have learned, now we have learned what is a galvanic cell, what are its components. We know what are the three important components. I would say three important components: the oxidation half cell, reduction half cell, and the salt bridge. So these are the three important components of your half cell. Okay, so whenever we are talking about electrochemical cell or a voltaic cell, this is how we show with the diagram. Okay, But how do you write this thing? How do you represent this entire setup in words? Okay, on paper, how do you represent this thing? So that is what we are going to learn. We are going to represent our electrochemical cell. We are going to learn how to represent the entire voltaic cell with a simple notation called as cell notation. We are going to learn something called as cell notation. It is also called as cell notation. Okay, so we have to follow the standard conventions that are given by IUPAC. So according to IUPAC, what are the standard notations and conventions that we have to use is, so whenever you want to represent a electrochemical cell, a voltaic cell on a paper, how do we represent this? So how to represent this is, so you just have to follow few techniques. Okay, so what is the technique you have to follow is, you have to start from here. This is the start point. Okay, you have to start from here. You have to start from where? You have to start from anode compartment. This is your anode compartment, right? This is your anode. So you have to start from anode and end up at cathode. You have to start from anode and you have to move towards cathode. And what is the direction in which you will be moving? The direction will be like this. So this is how you have to start. Okay, so this is the arrow in which you have to follow. Okay, you have to follow these arrows. So in this way, first you have to write down the electrode, then you have to write down the solution which is there in the anode compartment. Okay, then you have to go towards the salt bridge. Okay, then come down, then again go into the cathode compartment, solution, then finally you will come at the end. So this is the end. So this is how you will be working on this representation. So we have to start with the anode compartment, that too with the electrode, then its solution, then the salt bridge that we are using, then the solution of cathode, then the cathode electrode, the end. Okay, so let's write down that. So how do we write this? So first we have to start with the anode part. So at anode, what is that? We have the zinc. So first we have to write the zinc. So this is the electrode. What is this? The anode electrode. Anode electrode. So this anode electrode is solid, right? And what is this zinc sulfate solution? It is liquid, aqueous solution. So there is a change in the phase. So this is the solid electrode and dipped in liquid solution. So there is a change in phase, right? Solid and liquid. So to show that change in phase, solid and liquid, we use a slash. So this slash, what is this slash representing? Change in phase. So zinc in zinc sulfate solution. So this slash will tell us about what? Tell me the change in the phase, solid to liquid. I hope it is clear. So zinc electrode dipped in zinc sulfate solution. You can even write here ZnSO4, no problem, same thing. Zinc dipped in zinc sulfate solution. Okay, so next what? So next, let me write it as small as possible. Yeah. So it is zinc solid dipped in zinc +2 sulfate solution. Okay, right. What is the next one we are coming across? So this oxidation part, anode part is over. We are now entering into the salt bridge. So when we go for the salt bridge, we show it with the double lines. Okay, so this will represent salt bridge. So this 2/, this will tell us about the salt bridge. So this part is about salt bridge. So 2 slashes will tell us about there is a salt bridge present. Okay, salt bridge is over. Next, we are going into the cathode compartment with its solution. So what is present there? Copper +2. Copper +2. Okay, copper +2 in its aqueous form. Copper +2 in its aqueous form / copper electrode solid. So this is how you are going to show the entire setup. So this entire setup can be shown with this small representation, cell notation. So what are the things you have to mark it down here? The important things are, this is the anode part. Okay, this is the anode part. This is what? Tell me, the salt bridge. And this is your, this part is again, so this is your anode part, this is your cathode part. Okay. Okay. One more important thing is that you have to express them with the concentration also. That is very important. You have to also write down their concentration. So what is the concentration? Let's say the concentration of zinc sulfate solution is C1. What is that? C1. C1 means it is the concentration of this solution. Okay, and C2 is the concentration of this solution. So you have to mention the solution along with its concentration, C2. C1 and C2 are concentration of zinc sulfate solution, and C2 is the concentration of copper sulfate solution. Is that clear? So with their concentration, you have to always write down the concentration of the electrolyte that you have taken every time. So do not forget that. Always you have to mention. See, the mention of state is also very, very important. Mention of state is also very, very important. Okay, and this is going to give you a lot of information. First information that you're getting is this is the anode part and this is the cathode part, and you can see clearly what is happening here. So what is happening here? Zinc is converting into Zn plus 2 ion. So what is happening here? Zinc converting into Zn plus 2 ions is nothing but oxidation. Zinc converting into Zn plus 2, and here what is happening? Copper plus 2 converting into copper, means nothing but reduction. So the reduction half cell, oxidation half cell, followed by reduction half cell. I hope you guys are clear with this. So there are different ways. We will also come across different electrodes. There are electrodes, gaseous electrodes are there. Okay, whenever you come across gaseous electrode, you have to write down the gaseous electrode. See, here we are writing the concentration, right? Because it is an aqueous solution, liquid solutions. If you come across gaseous electrodes, you express their concentration in terms of their pressure, partial pressure. You have to express the concentration of the gaseous electrodes with their partial pressure. Okay, we'll be seeing that in the coming slides. So for gaseous electrodes, you have to express them in their partial pressure. So do not get confused. For gas it is partial pressures, and for aqueous solutions it is their concentration. So do not forget to mention their concentrations. It is very, very, very important. Okay, so please learn this part. Okay, this is very, very important because you will be coming across different kind of questions. You will be doing a lot of questions, because in the question they will be showing you this representation. They will not give you this one, they will be giving you this representation. So from this you have to collect all the information. You getting this point here? So why? Because we are going to learn Nernst equation. Nernst equation, whenever we are solving, the questions are given in terms of cell notation. So from the cell notation we have to grab all the information and use it for the Nernst equation. So is that clear? So this is very, very important. What is anode, what is cathode, what are their concentrations, and what is oxidation and what is reduction? I hope it is clear, guys. Everybody, any doubts from your side, please let me know. I hope you guys are following me. So till here it is clear. Very, very important topic. Very, very important topic. I would say the most important topic of this entire chapter. Okay, so this is very important. If you do not know to read what the cell notation or to write the cell notation, it's quite difficult for you to write down the next part. The next part, whatever we are going to learn, will be very difficult for you. So you have to learn what is oxidation, what is reduction, how to write down their reactions, and etc. Is that clear, everybody? Right then. Okay, this is what we have learned. So we have learned about the cell, what are their parts, what are what are the functions of each part, and how to represent an electrochemical cell. We have come up to here. So we have studied about the electrochemical cell. Now we have to see their applications. What does the use? Okay, what it is used for. So mainly it is used for what? Tell me. Finding out the EMF. EMF is nothing but the voltage difference generated. See, there is an oxidation half cell and there is a reduction half cell. Nothing but the negative end and the positive end. So between this negative end and positive end, you will have a potential difference. So this potential difference is going to tell us how much electricity are we going to generate from this redox reaction. Okay, so we have to calculate what? Tell me. We have to calculate the potential difference. That is called as a potential. The potential developed in this called as oxidation potential, and reduction potential. So the difference between oxidation potential and reduction potential will give us the EMF, voltage of the cell. So we need to learn what? Tell me. The electrode potential. I would say electrode potential, the oxidation electrode potential and reduction electrode potential. So we will learn what is oxidation, how to calculate oxidation potentials and reduction potentials, and with the help of this two, we will calculate the voltage of the cell, the EMF of the cell. Okay, right. So that is what the next topic we are going to learn is electrode potentials, because with the help of electrode potentials only we will be able to find out what is the total potential developed between these two potentials. What is the potential difference? So we need to find out the potential difference between the two electrodes to find out the voltage. So that is what we are going to learn, electrode potentials. So what are electrode potentials now? So electrode potentials are the tendency of an electrode. It is a tendency of an electrode to lose or gain electron. It is a tendency of an electrode to lose or gain electron. That is called as the electrode potentials. Okay, and it depends upon the concentration. It depends upon concentration as well as the temperature. Obviously, we keep the temperature constant. We do it at room temperatures. So keeping the temperature factor constant, it mainly depends upon the concentration. We have seen, no, what is that concentration? So this one. So it depends upon this concentration. Okay, we are talking about this concentration. So the potential developed here, it's called as oxidation potential. The oxidation potential developed here depends upon the concentration here. The reduction potential developed here depends upon the concentration here. Okay, so that is what. So it depends upon the concentration of the electrolyte taken. And what is the last one? Yeah. So we have two types of electrode potentials, that is oxidation electrode potential and reduction electrode potential. And what is that? It is the tendency, the capacity, okay, the ease with which they are getting oxidized or reduced. The electrodes are getting oxidized and reduced, right, in this particular cell. So at what ease? At what ease are they getting oxidized? At what ease are they going to get reduced? That is going to tell us about the electrode potential, the ease at which they can gain electrons and lose electrons. Okay, so that is what is called as electrode potential, the ease with which they can lose or gain electrons. Electrode potential. This is what. Okay, so this is what it is telling. So this is an electrode M, metal electrode. Metal electrode, how easily it is able to how easily it is able to convert into, from where to where? Metal electrode, the metal electrode solid converting into aqueous by losing electron. So this process, this tendency to convert into its ion. Okay, we are talking about what is this compartment? Metal converting into metal ion. It means we are talking about oxidation half cell. Okay, when we talk about reduction half cell, what happens there? It is a tendency at which it loses electrons, gains electrons, you can say. So losing electron, the tendency to lose electron and gain electron can be called as electrode potentials. And you can see here, so this potential, electrode potential, how the word potential they are using is electrode potentials, because see this metal, if you can see this is this is the positive part. Okay, this is the positive part, right? So when metal loses when metal is converting into metal ion, so this M converting into M plus ion, when the M is converting into M plus ion, so you can see that how this potential is developed. I'm showing you how this potential, why it is called as electrode potential, I'm showing you that. So this metal converting into M plus ions, right? So this M plus ions, where are they? Tell me. Just around. This M plus ions are around this metal ion, right? You will see the metal M converting into M plus ion means the metal electrode is surrounded by M plus ions. Can you see this? So there is lot of M plus ions you can see here. So if I remove this part, it's much clear. So what I was telling, so metal converting into M plus ions, if you see, so this metal ions are just around this metal electrode. Okay, and where are the electrons? Tell me. The electrons are over the electrode. So if you can see over here, so this metal is like your negative part. The metal electrode is negatively charged. We already have seen that the anode compartment is negatively charged, and you can see here this negative electrode which is there. Why it is negative? Tell me. Because of the electrons. So we have electrons over this electrode, that is why it is negative. And you have the positive ion. So you can see, so it means there are electrons over this electrode. So this is your negative part, and you have the metal ions in the aqueous solution, which is the positive part, right? So there is a potential. So there is a potential between these two things. Between these two things? What two things? Tell me. The negative electrode and the metal ions. So that potential is called as electrode potential. So oxidation, this is an anode compartment, right? So at anode compartment, you will see oxidation happening. So oxidation electrode potential means nothing but the potential developed between the negatively charged metal electrode and its metal ions. The negatively charged metal electrode and its metal ions. So metal converting into metal ions, you have the positively charged metal ions surrounding the negatively charged metal electrode. Same goes with your reduction half cell. In the reduction half cell also, you have the positive ions and the negative. So that potential is called as the reduction potential. So are you clear with this? What is electrode potentials? Electrode potentials are this. So how the potentials are developed? So this potential developed here is called as oxidation potential, and the potential developed in reduction half cell is reduction potential. Okay, clear? So what is electrode potentials? So the in easier way it is the tendency to lose electron and the tendency to gain electron is called as electrode potentials, right? So how do we measure them? How do we measure these electrode potentials? Since I have told you electrode potentials depends upon the temperature factor and the concentration factor, right? They depend upon temperature and oxidation and the concentration of electrolyte. So as we have learnt in our molar conductivity, there are some standard values, right? So here also we have some standard values. So we have to standardize this electrode potential because these electrode potentials will depend upon the concentration taken and the electrode taken and the temperature maintained. So whenever I talk about zinc dipped in zinc sulfate solution, I should be having a value which will tell us about, okay, this zinc electrode, so this zinc half cell is going to give me this much amount of potential. So there will be a standard oxidation potential values for zinc electrode dipped in zinc sulfate solution. Copper electrode dipped in copper sulfate solution, it will have a standard value. Those standard values are called as standard electrode potentials. Okay, so standard electrode potentials are nothing but the potentials developed at what conditions? Tell me. When you take a standard concentration of 1 molar, so you have to take a 1 molar concentration of electrolyte zinc dipped in zinc sulfate solution of 1 molar, zinc dipped in zinc sulfate solution of 1 molar at what is the condition? At 298 Kelvin. What is 298 Kelvin? Yeah, it's almost like an average room temperature, 298 Kelvin, because standard temperatures, room temperatures, we take it as 298 Kelvin. So at this condition, what is that? At a standard concentration and at a standard temperature, whatever the potential that we are measuring, that potential is called as standard electrode potential. Okay, so we need a standard value, right? Whenever we talk about zinc dipped in its solution means it should have a particular value. So whenever I take zinc half cell connected with copper half cell, since I know the potential value of zinc in zinc sulfate solution and copper in copper sulfate solution, it will be easier for me to find out what is the potential difference between these two electrodes, this oxidation half cell and reduction half cell. What is the value? To find out the voltage of the cell, I should know the standard values of each half cell, and that is this one. Okay, standard electrode potentials measured at standard concentration of 1 molar and at a temperature of 298 Kelvin. Okay, so this is called as your standard electrode potentials. Okay, fine. So we are taking these conditions to measure the standard electrode potential. But how do we measure? How can we measure standard electrode potentials? Okay, so by taking this condition, we are going to measure, but there is a problem. What is the problem? It has been seen that it's quite difficult to measure the absolute value of electrode potentials. You cannot measure the electrode potential. See, for example, if you want, see, there should be a reference, right? We should have a reference to tell. So they needed a reference to tell that suppose I have zinc dipped in zinc sulfate solution. Okay, it will have some electrode potential, right? It will show some electrode potential. So how much? See, what is this tendency? It is a tendency to lose electron and gain electron. So whenever we talk about some tendency, there should be some reference. So with respect to this is able to undergo oxidation more easily. With respect to this is taking some more time. It is less towards oxidation. So we should have a reference. So that is what we are going to see. It is quite difficult to measure. We need a reference. It's quite difficult to measure the reduction potential of a single half cell. If you just dip zinc electrode into 1 molar solution at a temperature 298 Kelvin, how will you measure it? Okay, how would you measure it? See, how do you measure? You can only measure with respect to something, because you can't measure the electrode potential with a single half cell. Always, whenever you want to measure the electrode potential with respect to something, because you can see in this half cell, see in this cells, if you can see, you don't have only, see, if you take only oxidation half cell, will there be any transfer of electrons? No, there will be no transfer of electrons. See, why this zinc electrode will dissolve? Tell me. Zinc electrode will dissolve as zinc plus 2 ions, because there is a requirement of electrons. So because of the requirement of this half cell is working. It means they are mutually dependent. Zinc is converting into Zn plus 2 ions and generating electrons. Why it is generating electrons? Because there is a requirement of electrons here. So copper plus 2 ions are waiting for electrons to convert into copper. So there is a requirement of electrons here. So that is why the zinc is converting into Zn plus 2 ion. It means this half cell is dependent on this half cell. And as well, same as that, this half cell is dependent on this. So they work mutually. They need other. So always this cell needs this, and this cell always needs this to complete it. So if you need a transfer of electrons, you need both of them working together, because it is a tendency to lose electron. How will you measure the tendency to lose electron? Okay, you can only measure the tendency to lose electron by with the help of this. So when in the presence of this half cell, at what rate zinc is, how easily zinc is converting into Zn plus 2 ion and giving the electrons out. So that is how we are going to measure. To measure the electrode potential of zinc dipped in zinc sulfate solution, we always need the cathode compartment, same as this one. So if you want to measure the reduction potential over here, you need the oxidation, because they work mutually. So it's quite difficult to measure the electrode potential of a single half cell. So we have to measure with respect to something. So what we are going to do is that we are going to find out the electrode potential with respect to something, right? So how will you measure with respect to something? I am going to take that, the one which I am going to take reference is this one. So there is a standard electrode called as standard hydrogen electrode, SHE. So I was telling you that whenever we measure the electrode potential, we measure it with respect to the tendency to lose electron or the tendency to gain electron is measured with respect to something. That with respect to something is nothing but this one. So this is the reference half cell. So whenever I want to find out the electrode potential of any half cell, I will connect this half cell with this thing. So this is the reference. Always we connect whichever metal's electrode potential you want to measure, you connect this half cell with this half cell. That's it. So you will get the potential difference. So this is called as the standard hydrogen electrode. So this is going to help us find out the electrode potentials. Okay, and let's see why we use this standard hydrogen electrode. One thing is very clear, that we use this standard hydrogen electrode to measure the electrode potentials of each metal electrode. Okay, and what is the standard hydrogen electrode? See, this you can call this, to overcome this difficulty, we need a reference electrode, and this reference electrode is nothing but the SHE, standard hydrogen electrode, SHE, or also called as NHE, normal hydrogen electrode. So this is going to help us. Why? Because we take the potential developed in this half cell as 0. We take this as our reference. We take this as reference because we take this as 0 volts. Okay, so for example, when you go to a shop, there is a weighing machine, right? And in the weighing machine, if you can see digital ones, so there is sometimes it is not calibration. You might have learned about calibration. So it is not always calibrated. It will show the weight of the container in which you are going to put the items. There will be one container, right? One heavy container will be there of at least 200 to 300 grams. So it means when you're putting this container onto that weighing machine, it will automatically show 200 and 300 grams without the item that you have put. So it means what? Tell me, it will be quite difficult for you to tell what is the actual weight of the item that you're actually weighing, because there is already 200 or 300 grams of that container which is already it is showing. So what do? The shopkeeper will calibrate it. Calibrate it means what? Tell me, he will make it as 0. So that is what, why he has made it as 0? Tell me, because with respect to 0, now you will be able to see what is the weight of the items that you are now going to buy. Same thing here. So if you're taking, instead of this electrode, if you take any other electrode, that particular half cell will have its own electrode potential. So it is quite difficult to measure the electrode potential of the unknown one with the known one. Okay, it becomes quite difficult. That is why what they have done, they have made the other electrode potential 0. So because we should always have two half cells connected, so the other half cell automatically they have made it as 0. So that is how you can take this example of your shopkeeper. So when you go to a shop to weigh something, he will make it as 0, although there is some weight of that copper, weight of that container weighing. So I hope you guys are clear with that thing. So we have made one of them 0. So that 0 is nothing but standard hydrogen electrode. So we are going to take the help of this half cell to measure the half cell, to measure the electrode potentials of the other half cell. That is the use of this. And what is the use of this hydrogen electrode? Is one use is this one. What is that? Its electrode potential is taken as 0 volts. So with respect to 0, how much value is the other one? Okay, so that is one. This is one advantage. What is that? It is arbitrarily taken as 0 volts. And what is an hydrogen electrode? It's very important to know what is an hydrogen electrode. It is the hydrogen electrode dipped in 1 molar solution of acid, 1 molar HCl solution at 298 Kelvin. Same standard conditions. We are using the standard electrode, right? We are going to measure the standard electrode, means we are going to use the standard conditions, 1 molar and 298 Kelvin. In this, you can see that there is a hydrogen gas pumped into this electrode, nothing but with a platinum wire. So there will be a platinum wire along with the hydrogen gas pumped into 1 molar HCl solution. So 1 molar HCl solution, hydrogen, it's called as hydrogen electrode. I told you some gaseous electrodes are there, right? This is that gaseous electrode. So this is how you will see the gaseous electrode. Mostly you will come across hydrogen electrode as the gaseous electrode. And hydrogen electrode is a very special arrangement. You will have a platinum wire. We will have a platinum wire in the tube, and around this platinum wire you will have the hydrogen gas. You can see this. This is a glass tube with a platinum wire, and you have the gas inside this. That is your hydrogen electrode dipped in 1 molar aqueous solution at 298 Kelvin. So this is the arrangement of your SHE, standard hydrogen electrode. So already we have seen one point, that this is going to, we are going to take its electrode potential as 0 volts. Okay, what is the next important point is that this this electrode potential, this standard hydrogen electrode has one more important thing, that it can act as both cells. It can act as the reduction half cell as well as the oxidation half cell, because what I told you, tell me, I am going to connect the half cell, the metal half cell, of which we have to measure the electrode potential, with hydrogen electrode, right? So this hydrogen electrode, which I am going to use as my reference, has a dual nature. What is the dual nature? Tell me. It can act as anode as well as cathode. So that is the second importance of this hydrogen electrode. Already its electrode potential is 0, and it can act as dual. It has dual character, that is, it can act as both the anode compartment and the cathode compartment. Okay, I guess the time is already up. So we will continue with this SHE and how to measure the electrode potential. So you can see here, this is the SHE compartment, and this is the reference, and this is what I am measuring. So if I want to find out the electrode potential of copper, what I will do, I will connect it with SHE. So automatically I will get to know to measure, I will get to know what is the electrode potential of this unknown metal electrode. So this is how we are going to connect it with SHE. Okay, this is these things we'll be learning in the next class. Hope this session was informative, and this is very, very important class, and the next class is going to be even more important, because we are going to learn Nernst equation in the next class. Okay, so I request everybody to go through your NCERT book, read each and every line, make a notes of this, go through the class, and then you will get each and every concept very clearly. Okay, hope this class was informative. Thank you for your session. Thank you for your time. Thank you very much, and have a nice day. Have a great day. Thank you. Bye bye. Take care.